My name's Alan Ho. I lead our product management at the Google Quantum AI team, and I'm today very excited to talk about the new tools that we have for quantum algorithms research. You're probably all here very excited about the recent hardware advancements in quantum computing, but the challenge is looking for useful algorithms is often a time-consuming and a very expensive task. So today I'm going to tell you a bit about some new tools that we have for you that you can use find useful quantum algorithms for noisy intermediate scale quantum computers. So let me first start off and give a little bit of context. Google is embarking on two grand experiments. The first experiment is the experiment of application discovery using our computers that we have today, such as the Sycamore processor, which we use to demonstrate the world's first beyond classical computation. The second experiment that we're working on is trying to build an error-corrected quantum computer in 10 years. And for this particular talk, for the error-corrected quantum computer, we have a really good presentation tomorrow with our hardware team leads. So with regards to tools for application discovery, we really have two sets of tools. The first set of tools are open source tools, and these are various tools built on top of the foundation of Circ. This Circ is a software platform software framework that we open sourced about 2 years ago, and we're starting to get a lot of adoption by an ecosystem of libraries that will help you discover new applications. The second tool, which we'll talk less about today, is our quantum computing service that we are allowing people to access via the cloud. We've used it for our own research. Some of those papers have already been published in science, and we hope that when we have more results from our collaborators, these the first early sets of users, we will be sharing that with you in the future. The first tool I'd like to talk about in our ecosystem is QSIM, a high performance quantum circuit simulator, which is the ability to simulate a quantum computer on a regular classical computer. And I want to provide some motivation for this. When we're comparing classical processors versus quantum computers, we always will we the- it's a little bit difficult because today's quantum computers, with the exception of the random circuit sampling algorithm, are significantly less powerful than classical computers for the algorithms that we know about today. So the question is, how do we project whether the algorithms we're discovering today will be useful beyond when our quantum computers get better? So what you want to do is when you're testing your algorithms, you would want to take a look at how when you're testing your algorithms on a quantum computer or in these simulators like QSIM, you want to ideally see an exponential speed up, meaning that as you increase the number of qubits, the amount of classical compute requirements goes up exponentially. Now, a little bit less ideal is if you get a polynomial speed up or a quadratic speed up. So meaning that as you increase the number of qubits or the size of your quantum computation, the classical requirements goes up quadratically. And what you really don't want to see is this linear speed up, meaning that you increase the size of the number of qubits linearly, and then you increase the size of your qubits, and you see only a linear speed up. Because at that point, you really don't have any need to even use a quantum computer in the first case. So if you look at this, unfortunately, when you use low number of qubits, it's very, very difficult to distinguish between a linear speedup versus an exponential speedup. So being able to test your algorithms on more qubits allows you to essentially draw more plots on the line and gives you more confidence in the algorithms that you expect worked on. And this leads us to QSIM, our high performance quantum circuit simulator. It is a full wave function simulator, also known as a Schrodinger based simulator, meaning that the performance is much more a function of the number of qubits rather than a function of the depth of the circuit. It's high performance. It uses Intel advanced vector extension codes. It's highly multi-threaded. It works very well on multi-core processors. It uses OpenMP underneath the hood, and it has this concept called gate fusion, which means that you can have multiple 2-qubit gates fused into one much larger gate and execute on the processor at one time, and it gives us another boost in speed. It's also what we use to benchmark our quantum supremacy experiment. So it's really been, sorry, our beyond classical experiment we did last year. So it's really used. We've kind of battle hard tested it, and we've used it in a very large grid computing setup. We've made it compatible with Circ. So if you write your applications in Circ, it's immediately compatible with QSIM. And from a cost perspective, we were able to run 40 qubits, circuits of 40 qubits on Google Cloud Platform with 9 terabytes of RAM within a few hours. And so this is highly efficient and highly useful. And we think that by focusing on a single server and making it as performant as possible, this is kind of a sweet spot where you want to be testing your algorithms from a circuit simulation standpoint. And this is due to once you go across, once you're trying to simulate a circuit across multiple computers, you start eating a lot of overhead in terms of network communication. So from a code sample standpoint, it looks exactly like how you would write Circ code, with the exception of a line of code that uses this QSIM simulator instead of Circ's internal simulator. And to kind of demonstrate this, I want to give you a live demo um, showing you how you could progressively sample larger and larger quantum circuits, random quantum circuits. So on the right here, you see a very non-trivial probability distribution function, which was created from sampling those random circuits. Okay, so just to give you a quick plug, by the time you see this video, our website would have launched. This is a place where you can discover all that software tools that we have. You'll be able to see things like Circ, our open source tool like QSIM, and it has really nice tutorials. And I'm going to kind of jump over to a demo right here. So over here, I'm going to benchmark, run for you a 20 qubit simulation. This quantum volume of about 1 million, and we're going to compare Circ versus QSIM and how fast it would be. One thing to note here is that this is running in a Colab environment. This is Google's hosted Jupyter Notebook service. And basically, this gives you 1 vCPU of compute power. But even on that 1 vCPU, we can look at the difference between Circ and QSIM. We see almost a 60x speed up for that. Now let's go a little larger here. Let's try 25 qubits. And because it's going to take a long time in Circ, we're just going to skip that. So while this is running, one thing that you'll wonder is why can't we use more? What have we actually have a larger number of CPUs? So what I'm going to demo to you here is very similar environment. What we've done is we spun up a 40 vCPU instance in Google Cloud. This has, I believe, about 900 gigs of RAM. And through the Colab, what we can do is that we can connect, if you see here, we can connect to that GCP instance I just showed you through routing through my laptop and forwarding and SSHing into that computer. So we've set up some port forwarding already. And I've kind of set up already so that we can do this demo. So we just saw previously it took 9 seconds, and let's see how fast we can when we do work on a 40 vCPU computer. All right, 2.3 seconds. So that's quite a bit faster. All right, and one last demo I'm going to show you here is we're going to try doing a much larger circuit. So this is a This circuit, last one over here, is a 32 qubit circuit with a gate depth of 14. This time we're going to use um, the same computer, and we're going to launch we're going to launch the simulation, and we're going to take a look, come back and take a look at how long it actually took. Okay, let's go back to the slides, please. So with that, the second tool I'd like to introduce to you is TensorFlow Quantum, which is our open source machine learning framework. To give you some context, there is a type of algorithm called quantum neural networks that leverages the qubits and the gates within the qubits to simulate the operations of data flowing through a neural network. So in some sense, the parameters or the rotations are very analogous to the weights between each layer of neurons being executed. This was discovered by Hartmut Nevin and Edward Farhi from our group several years ago, and we ran with that and created a framework. Using this base quantum neural network, one of the very promising architectures for it are these hybrid models on quantum data. And let me explain that a little bit more. We believe that if you are operating a quantum neural network on quantum data, meaning that the data has natural amount of entanglement and that could feed directly into the quantum computer, um, our quantum neural network would have an exponential advantage over processing it on a classical computer. Furthermore, because these are noisy circuits, it's beneficial to lower the gate depth for your quantum neural network. And one of the ways that we could do that is we can feed the data into a classical neural network and leverage both a combination of a quantum and classical neural network to when we're doing our predictions. The challenge around that, however, is that it becomes pretty complex. Whenever you're doing any training and optimization, you'll need to do things like backpropagate through the classical and quantum neural network. And so TensorFlow Quantum is the framework that we built for that. And it looks very similar. If you've played around with TensorFlow and you know it very well, um, our software is very, very compatible with the existing extractions. So specifically Keras, all our layers are very similar to Keras. So you would basically program these layers using a little bit of circ code, and it would just look like Keras. And when you execute the quantum circuit, you can execute it either on a classical computer through the TensorFlow execution engine. Underneath the hood, it actually uses QSIM to execute the circuits, or you can execute it on a quantum computer through circ. This is kind of give you a schematic, a kind of flavor of what it looks like. So you can see three layers of circuits: one for the data, one layer of the circuit, one layer for the layers for the neural network, and then layers for the classical neural network, and it's all kind of like put together. So to give you a demo of this, I'd like to do use TensorFlow Quantum to do a binary classification of a multi-qubit quantum state, specifically the cluster state. Can you head over to the demo? So again, if you want to learn more about this, you can check out our website, TensorFlow/Quantum, and you can learn a little bit more about some of these demos that I'll be showing you right now. So let me kind of give you a quick understanding of what this problem is going to be. What we want to do is that we want to prepare a cluster state. These are basically entangled states, and we want to train a quantum neural network to distinguish if a cluster state is excited or not. An excited state basically is on one of the qubits in the cluster state, you do an X rotation and you excite it from a 0 to a 1. And basically, we're going to see if we can actually figure out. So you rotate it by 180 degrees. So from a TensorFlow perspective, what we're doing is that we're constructing various layers, and then we are in those layer. This is the data preparation layer, and the data preparation layer consists of the preparing of the cluster state and doing an X rotation on one of the qubits, randomly on one of the qubits, so that you have excited states or not excited states. And then followed by a convolutional neural network, quantum convolutional neural network layer, followed by calculating the expectation value from that neural net. So we're reading on one qubit. And we use this to train the quantum neural network to detect the cluster state. So I'm going to kind of, so over here you can see we're kind of preparing the data. And then we define the various layers. So this is the data preparation layer. This is the QCNN layer. We're basically building small little building blocks for this quantum circuit. And then we're assembling these convolutional layers, and then followed by these pooling layers. And when we construct the actual circuit itself, it's basically, we are basically using all those various building blocks and layering them on top of each other, very much like Lego. And so if you look at kind of the output, as you can see here, we could use the Keras utilities for this. What it's showing you here is that it's taking the cluster state data, cluster state. It's creating a tag on it, whether it's so for cluster states that are excited, it's putting a excited tag on it, and it's separating out the data into both training data and validation data. And then when we train the model, very similar to training a model in TensorFlow, we just execute it and it has these epochs. And you can see here, we can actually we can plot to see that the quantum convolutional network is gradually getting better after overtraining over a certain number of epochs. Now, if we want to go to the next level, we can try using a hybrid quantum neural network. In this case, it's almost exactly the same as the previous one, except that instead of reading out from one qubit, you're reading out from two qubits, and you're putting that information into a neural network, a classical neural network. These are dense layers in Keras. And very similarly, you can construct the model, and you can see here, we're appending uh, dense classical layers on top of our quantum layers. And so we get a format somewhat like this, where we have the data, it's going into our quantum neural network, and then it's being fed into a dense neural network. And when we execute and train the model and we plot it out, you can see here that our hybrid quantum convolutional network is achieving a validation accuracy much faster than our quantum only neural network, which means that you need less training time, and meaning that this probably has better learning ability than a quantum only neural network. So the net takeaway is that with a very modest classical assistance, your hybrid model will converge much faster than quantum. All right, so before we actually just jump to back, I just want to show you, before we jump back, I just want to show you that let's see how long it took for the 32 qubit experiment. Oh, wow, great. It took 204 seconds. So that's about 3 minutes for a 32 qubits quantum circuit simulations, which is not too shabby at all. Let's go back to the slides. So I want to give you a description of how we could put this all together. We recently published a paper called "The Power of the Power of Data in Quantum Machine Learning," which explores the necessary conditions for data to have a quantum advantage for quantum machine learning. And we wanted to push the simulations and verify our results at the 30 qubit level. And to do this, we use 101 large GCP machines. That's around 11,000 vCPUs. We use Docker and Kubernetes to manage the cluster. And we use TensorFlow distribute strategy in order to parallelize the training of these neural networks. The result was we were able to manage to execute hundreds of thousands of circuits within a few hours and achieve a petaflop scale computation. Specifically for the quantum circuit simulation, we hit about 296 teraflops of sustained performance just for QSIM alone. Next slide. And if you are interested in this area and you want to learn more, we have even more tools from various collaborators, companies like Xanadu, who are doing machine learning algorithms, universities like Zapata, and national labs like Sandia. And so we have a variety of various tools for you to try out. And if you want to learn more about this, go check us out at our website, quantumai.google. Thank you very much.